And now we have time for questions. Just do not forget to unmute your microphone.
Yes, may I make a comment?
Yes.
John Pendry speaking. Hi, David. I enjoyed your talk, but there are some historical facts I want to put you right on. The first thing to remark is that Besolagos's lens, as described by Besolago himself, was discussed entirely in the context of the ray approximation.
Yes.
And he had nothing to say about Maxwell's equation solutions, nor did he have anything to say about the electrostatic solutions, which were the first part of your talk. And I want to point out to you, because it wasn't obvious from what you said, that my paper in 2000 was the first time ever that the possible perfection of the Besolago lens was mentioned. And although you were somewhat derisory about multiple scattering theory, it is an exact theory and an exact solution of Maxwell's equations. And the conclusion of the perfection of the lens was exact. And it was the first time that that conclusion was come to. Also, when you talked about the Zhang experiment, you failed to mention that it was actually based on a suggestion in my paper that you could use a slab of silver to approximate the perfect focusing. So I think, particularly for the younger people in the audience, it's important that we get history correct.
Thank you.
So thanks. Do we have other questions?
Yes, I have one question.
Yes, Emil.
So it's about this volume V1 where the scalar product was defined. So then to understand that, in fact, you can compute the fields only inside that volume V1?
No. The usual Hilbert space expansion starts, of course, only from that subvolume, because the eigenfunctions are all divergence free. You can only use them to expand a physical field that is divergence free. And if Jx vanishes inside V1, then inside V1, all the physical fields are divergence free. But then, in order to get results for the physical field also inside V2, what I do is I substitute those expansions which are only correct in V1, I use them in Maxwell's equation, where the difficult part in Maxwell's equations are where you have the theta 1 times one of these eigenfunctions, and then
yes, the fields can be extended.
Yes, and then you find, I didn't show all the algebraic details, but then you finally get an equation that is equivalent to Maxwell's equation, and that includes the field everywhere.
So then my follow-up question is, if you try a numerical check to see how stable the procedure is, especially for situations where the boundary is not smooth like a sphere, but let's say something more wiggly.
Yeah, no, I did not try that. That should be tried, of course. The thing that I did do, both in the quasi-static case and more recently in the general case, is for a flat slab. For a flat slab, of course, it agrees very well with the results of John Pendry. For a sphere, I applied it to a calculation of the scattered field when the incident field is a plane wave incident on a single sphere. And that's a calculation which it can be done using classical methods. And in fact, it's done in the textbook of Jackson, and we get exactly this, well, in the appropriate limit, we get exactly the same results.
Mm-hmm. Thank you.
But of course, for an interface that has sharp corners or touching points, that still needs to be done. But of course, a very interesting application is when you have two metal spheres which are very close to each other, and then if there are atoms or molecules near the small distance between the two spheres, you can get very strong Raman scattering, or also very strong emitted field if the molecule or atom is excited. And those are situations that can be easily handled by these eigenstates, because there's just two spheres. Even if they are close by, it's very easy to calculate the eigenstates of a combination of two spheres or even a small number of spheres.
Mm-hmm.
Okay, thank you, Emil. Is there any other question? So I am just checking the chat if there is anyone else asking. So apparently we do not have more questions. So I would like to thank Professor Bergman once again for the nice talk. That will be that was recorded, and it will be available online in the coming days. So you can always watch it again on our webpage. And I would like to just to mention to all the people from the audience that at the moment there is something that is looking like a conference with a very similar name to ours, called the MetaMAT's 21, apparently happening in London. It was not advertised, it's not organized by us. It's just some conference, some people just making money and constantly getting the list of our speaker to try to sell the conference. So it's just that you know that we are not part of this business, and we are not, they have just used our name to promote their webpage. But you will see very easily yourself that the fees are between 600 and 4,000 euro for the registration, so that you don't get inside of this trap. Thanks again for all of you for attending this webinar. I think Sebastian, you raised your hand.
Yes, maybe we would like also to advertise the fact that next week it will be Professor Ross McPhedran who will be giving a talk. The title will be announced very soon, and as everybody knows, Professor Ross McPhedran has contributed quite a lot also to the theory of light and periodic structures. That's all.
Okay, thanks,
Very high quality subtitles. Very high quality subtitles. Great.
Okay, thank you, everyone, and see you next week.
Thank you.
Bye-bye.
Bye.
Thank you. Bye.